video is going to teach you how to address questions that deal with temperature and pressure changes for a gas. And that is called gay-Lussac's law. Now, before we get into the law, just a reminder, when we do these basic gas law calculations, we are dealing with volume, pressure, and temperature. Typically, one of those three variables is held constant and the other two are changing. We will see in the next video an example where everything is changing. For this video, temperature and pressure could change, but we are going to assume that our volume is held constant. And again, your clue that something is held constant is either maybe it's not mentioned, they will give you a volume that will never change, or they just may outright tell you that the volume is constant. But everything else is going to be pretty much like the Boyle's law and the Charles law calculations that we have already done. Very simple, very straightforward. Keep in mind, again, that temperature must be plugged in Kelvin. So if they happen to give you a temperature in degrees Celsius, make sure you add 273 to convert it to Kelvin before you actually solve the problem. If they ask you specifically for the temperature in Celsius, you just convert back to Celsius at the end by subtracting 273. So that said, let's take a look at gay-Lussac's law. The pressure of a confined gas increases with increasing temperature. This is why aerosol cans sometimes post warnings such as, do not expose to temperatures greater than 140 Celsius. All of you have probably seen this before. And when we are doing this law, we are assuming, again, that the volume is not changing. Think of an aerosol can. When you have an aerosol can, that is what we would call a rigid container. And if you start heating that can up, the pressure inside that can is going to get higher and higher until the point where the pressure of that gas overcomes the integrity of the structure of the container, in this case an aerosol can. And in that case, it's going to find a weak point in that can, and that can is going to bust. So keep in mind, we're talking about a rigid container here, a container that's not, let's say, flexible. Like a balloon, if you increase the temperature in it, its volume can actually flex. It's going to be able to move. If you have a rigid container and you've got a gas inside of it and you start increasing the temperature inside that container, those walls aren't moving. And in that case, the pressure inside of the container is going to start building up. So an aerosol can is a great example of this. There are lots of other examples out there. Now, this law states that the pressure of a sample of gas is directly proportional to the absolute or Kelvin temperature when that volume remains constant. So what that means is if you increase the temperature, the pressure is likewise going to increase. If you decrease the temperature, the pressure is also going to decrease. You could also look at it this way. If you double the temperature of a gas, the pressure inside of that container is also going to double. If you quadruple the temperature of the gas, the pressure inside the container will likewise quadruple. So that's just another way of looking at this law. So let's just write down what we know. So for gay-Lussac's law, we are only interested in temperature and pressure. And as temperature goes up, pressure goes up. As temperature goes down, pressure goes down. So we are assuming that volume is constant. That means the volume is not changing, and we can underline that as well right here in the notes. And this is definitely some information you would want to have in your notes. Hopefully you're pausing, especially if you're one of my students and you're writing this stuff down. Now, the formula for gay-Lussac's law is as follows. Pressure 1 over temperature 1, and I bet you could guess the second part because you've already seen this in other videos. Our ones are always on the left, so what's on the right? 2's. I know you said it, so I'm going to say good job. So pressure 2 over temperature 2. Something else you might have noticed from Boyle's, Charles, and gay-Lussac's laws, now that you've seen all three. Not only are 1s always on the left and our 2s are on the right, have you noticed that if we have a pressure or a volume involved, it's always on top, and if we have a temperature involved, it's always on the bottom? That's going to be important when we do the next video, which is combined gas laws. All right, so let's take a look at our first example. A cylinder of gas, and when you think of a cylinder, think of like a metal container that's not flexible in any way. It's not going to move, like an oxygen tank perhaps, or a helium tank. A cylinder of gas has a pressure of 103 kilopascals at 25 degrees Celsius. Do you see how these two go together? That word at's kind of a big clue there. 103 kilopascals, which we know is a measurement of pressure, by the way, at 25 Celsius. So this is my pressure 1 and my temperature 1. Now, I already know that I cannot work with a temperature that is in Celsius. I'm going to change that to Kelvin by adding 273. And 273 plus 25 is 298 K. So I'm just going to go ahead and make a note of that. At what temperature will the pressure reach? 109 kilopascals, that is P2. So obviously they are asking me for T2 because that's the only piece of information I don't have. Nowhere in this problem did they mention volume, so I'm going to assume it's constant. That would make sense. If you have a cylinder, it's got, whatever. Let's say if you were looking down inside of it, that's how big around it was. That's its volume. It's not going to expand. It's not going to contract. If it's a metal cylinder, that volume is staying the same. So we already know if that temperature starts going up inside, that pressure is going to go up. If that temperature goes down, that pressure is going to go down. We are ready just to write down this law, rearrange, and plug in. And you guys who've been following me know that's how I love to do these problems because then everything has a place. So let's write down our formula and rearrange it. We have pressure 1 over temperature 1 equals pressure 2 over temperature 2. Now, for this particular problem, I am solving for T2. Let's pretend like math is not your thing, so we're going to circle T2. And if you'll remember, I've mentioned in other videos, when you have fractions like this, just cross multiply to get everything on one line. It's going to make your life a lot easier. Because I want this T2 on the left, I'm going to do this first. So that is T2 times P1, and you know the order you write those in does not matter, equals T1 times P2. That's so nice because now everything's on one line. I can see that I'm still trying to solve for T2, but now it's really easy for me to see how to get T2 by itself. And I'm going to divide both sides by P1. So my formula is, and y'all know I got to be a little extra here, T2 equals T1 times P2 over P1, and this is my formula that I'm going to plug into so that I can perfectly solve for that second temperature. So let's go ahead and plug this in. T2 equals T1, which was 298 K. Let's see if we can get all that in there. 298 K times P2, which was 109 kilopascals, over P1, which was 103 kilopascals. Kilopascals cancel. Again, I can't say this enough. I love plugging everything in where it goes because I'm not having, if I would have plugged in here, that's okay. And a lot of people are really good at that, but then I'm moving numbers and units. If I get it set up, I can just put everything exactly where it goes. I can cancel out very easily. I can see what cancels out. I'm left with Kelvin. That's a good thing because I am solving for a temperature. So I'm going to go ahead and multiply 298 by 109, make sure you hit equals, divided by 103. And when you punch all that in, you should get about 315.36 Kelvin. Now, let's ask ourselves, does that answer make sense? So let's look back up at the original problem. I had a pressure of 103 kilopascals at 25 degrees Celsius. It looks like the pressure went up to 109. So if the pressure went up, that tells me that temperature also went up. Now here's the thing though. That temperature is in Celsius and this is in Kelvin, so that's a little bit hard maybe for me to compare. Do you know how to get that back to Celsius? Yeah, you could just subtract 273. So let's see what that was in Celsius just so we can compare apples to apples. 315.36 minus 273. That's going to be 42 degrees Celsius approximately. I'm rounding a little bit. So yes, the temperature went up from 25 to 42, so it makes sense that the pressure would have gone up from 103 to 109. Also, you did know, we didn't have to do that. I just want to show you how to convert back at the end. But we already had T1 right here in Kelvin, and you could see it went from 298 to 315. So what I wanted you to see there was you can compare it Kelvin-wise or Celsius-wise, but they're proportional because you've just added 273 or subtracted 273. So everything works out. Let's do one more example of gay-Lussac's law. Again, if you are following along at home and you're just like feeling really good about this, go ahead and copy this down, maybe try it yourself, and then we will do it together. So this example says a cylinder of gas has a pressure of 4.4 atmospheres at 25 degrees Celsius. I can see that these go together. This is my pressure 1 and my temperature 1. I know that I cannot work in Celsius, so I'm going to add 273 to that. That is 298 K. Also, you might notice in the first example, we were working with kilopascals, which is a unit of pressure. Atmospheres is also a unit of pressure, and you still treat the problem exactly the same way. You're starting with atmospheres and ending with atmospheres, just like in the previous problem, you started with kilopascals and ended with kilopascals. So what I tell my students is, for problems like this, whatever pressure they give you, just run with it. At what temperature in Celsius, now they are specifically asking for a Celsius here, I need to remember that at the end, will it reach a pressure of 6.5 atmospheres, and that is going to be my pressure 2. So let's write down our formula. By the way, I do not see any volume mentioned in there, so what am I going to assume? I'm going to assume it's constant. So P1 over T1 equals P2 over T2. This time I am solving for T2. I'm going to circle that, and I'm going to cross multiply to get everything on one line because that is how my brain prefers to look at this problem. T2, P1, some of you very advanced math students are probably like laughing at that, but it's a good way to do it if you're not a math person, which I am not. T1 times P2. All right. I like this because everything is on one line. I am still trying to solve for T2, but now I can very easily see how to isolate it. I'm going to divide both sides by P1. I now have my formula ready to go, so I'm going to write it out neat. Be a little extra here. T2 equals T1 over P2 divided by P1. Temperature 1 was 298 Kelvin. Pressure 2 was 6.50 atmospheres. Divided by pressure 1, which was 4.40 atmospheres. Everything is neatly in its place. Atmospheres cancel. I am left with Kelvin. That is great news because they asked me to solve for temperature. So let's multiply everything on the top together. 298 times 6.5 equals, divided by 4.40 equals, I'm getting 440.23 Kelvin. All right, Let's take a look at that and see if that looks like a reasonable answer for this problem. I started off with a pressure of 4.4 at 298 K. It looks like the pressure went up to 6.5 according to the problem, so I am guessing that my temperature went up from 290 K, and it did. And it looks like proportionally, you know, it looks like maybe we went up by like about a third here. It also looks like we went up by maybe a little more than a third here too. So that answer looks reasonable to me, so I know I'm probably right. I know I'm probably right for two reasons. One, the answer looks reasonable, and two, all the proper units canceled out. So that is not 100%, but that's really close to a good guarantee that you've got this problem correct. There is one more video in the basic gas law series, and that is going to be the combined gas law, and that's going to be the next and fourth video in this series, and then we will move on to the ideal gas law.